Welcome to the Composite Intermediate Bulk Container IBC webinar. Chris Lind, formerly of Mauser USA LLC, originally presented this webinar. We'd like to thank Mr. Lind for all the work he did in putting together this presentation. Today we are going to discuss composite intermediate bulk containers. We'll review the definition of composite IBCs, look at the components, performance-oriented testing, and UN DOT markings. We'll also look at certain special applications, including permeation barriers and IBCs intended to hold flammable and combustible liquids. An intermediate bulk container is rigid or flexible portable packaging other than a cylinder or portable tank designed for mechanical handling. An IBC has a volumetric capacity of more than 119 gallons or 450 liters, but no more than 793 gallons or 3,000 liters. The material used for construction may be metal, plastic, fiberboard, wood, flexible, and composite. IBC UN codes include 31A, 31H2, 31HA1, and others as noted in the slide. Intermediate bulk containers are used across a wide range of industries for liquid transport and storage, including paints and coatings, petrochemicals, fragrances, foods, and pharmaceuticals. RIBCA, the Rigid Intermediate Bulk Container Association, fosters the interests of persons, firms, and corporations engaged in the business of manufacturing or assembling rigid intermediate bulk containers. There are currently 7 producing members, conveniently located across the United States. The IBC Packaging Type 31HA1 is a composite IBC with a plastic inner receptacle and steel outer receptacle. IBCs in the United States range from 135 to 330 gallon capacity. Internationally, 275 gallons or 1,000 liters is the global standard. This slide illustrates the various parts of a composite IBC. The body is also known as the inner receptacle and sometimes called the bottle. Service equipment refers to the equipment attached to the IBC that is used for filling, discharge, pressure relief, safety, heating, insulating, and measuring components. Structural equipment is the portion of the IBC used for reinforcing, fastening, handling, protection, or stabilization, such as the pallet and the cage. This slide provides more detail on the components of an IBC. The inner receptacle is typically extrusion blow-molded from high-density polyethylene. The bottle will have an opening of 6 or 9 inches for filling and is closed with a cap. The cap may have additional openings in it. IBCs are available in 275-gallon capacities with 2 additional 2-inch ports, one over the valve and one 180 degrees from that for special applications where one might want to use dip tube, extraction tube, or level indicating probes. Most IBCs come with a rigid welded galvanized steel cage or a chrome-plated or powder-coated steel cage. The cage is designed to withstand the dynamic and static load placed on top of the filled IBC. The inner receptacle of an IBC is thinner than a plastic drum because the steel cage provides the needed strength and is designed to withstand the top stacking load. Typically, IBCs have a 4-way entry pallet to assist with handling. The pallet can be a composite, steel and plastic with steel reinforcement, all steel, and wood. IBCs generally have a discharge valve, and they are available in different sizes and styles. Corner protectors are used to protect the inner receptacle from accidental damage, for example, forklift hits. While IBCs can be ordered without corner protectors, that reduces the UN rating. Common accessories on IBCs include valves which are installed for discharge of the IBC's contents. The most commonly installed valves on an IBC are the butterfly valve and the ball-style valve, with the cylinder valves being the third most common. The valves are typically all plastic with a metal collar or are welded. The most common type of valve is manufactured from high-density polyethylene and is screwed in or welded in place. Valves are also available in glass-filled polyethylene and glass-filled polypropylene material. The nominal sizes for valves are 1.5 inches, 2 inches, and 3 inches. Another accessory for an IBC is a cap. Caps are available in 6 and 9 inches. Caps can be solid or have 1 or 2 additional openings. Caps can be vented for pressure and/or vacuum relief. Caps can also combine ventilation options. Vents are required if the lading generates vapor pressure that could cause failure, but may not be vented if the venting creates a hazardous atmosphere in transportation. An IBC will have marking plates, sometimes called label plates, made of steel or plastic and are available in many different sizes. It should be noted that on an IBC used for hazmat or dangerous goods, 2 plates on opposite sides are required. Performance-oriented packaging testing of IBCs is required by federal law if the IBC is intended to contain hazardous materials. The testing and subsequent marking of the IBC are proof that the package will safely contain hazardous materials and be able to withstand normal conditions incident to transportation. The packaging manufacturer is responsible to ensure each package is capable of passing the prescribed tests. A packaging's assembly function, including final closure, is to be performed by the person who offers hazardous material for transportation. The final closure needs to be done according to the packaging manufacturer's instructions. The user should note that if a person is using a 6 or 9-inch cap with a 2-inch plug, that both the cap and the plug must be closed according to the manufacturer's instructions. A UN-rated intermediate bulk container must pass required testing as specified in Title 49 of the Code of Federal Regulations 178 Subpart O, contingent on the design type. Design qualification testing requires the following sequence of tests in the order given. It should be noted that with drums, you can use fresh samples each time. When testing an IBC, only 2 samples are allowed. 1 sample is subjected to a drop test with height based on the specific gravity of the intended lading. The second sample must be subjected in order to a vibration test, a bottom lift test, a stacking test, a leak-proofness test, and a hydrostatic pressure test. This slide illustrates the drop test procedure for IBCs. The IBC is filled to not less than 98% of its rated capacity with a water and antifreeze solution. The testing is carried out when the temperature of the IBC and its contents has been reduced to -18 degrees centigrade or 0 degrees Fahrenheit or lower. The IBC must be dropped onto a rigid, smooth, flat, and horizontal surface. The point of impact must be the most vulnerable part of the base. Following the drop, the IBC must be restored to the upright position for observation. The drop height for an IBC would be anywhere from 0.8 to 1.8 or 1.9 meters. The vibration test is conducted on a sample IBC filled with water to not less than 98% of capacity. The IBC is placed on a vibration platform with a vertical or rotary double amplitude and subjected to vibration for 1 hour at a frequency that causes the packaging to be raised from the vibration table so that a piece of metal, 1.6 millimeters thick, can be passed between the bottom of the IBC and the platform. An IBC passes the vibration test if there is no rupture or leakage. EU regulations and UN model regulations also add, quote, "no broken welds," end quote, as a criterion for passing. The next test is a bottom lift test. The IBC is filled and top-loaded to 1.25 times its maximum permissible gross mass. The forks of the lift truck are put in centrally positioned 3/4 of the way through the bottom so that the IBC hangs precipitously from the forklift to simulate poor handling. Next, the IBC is lifted clear of the ground twice from each direction. All composite IBCs with outer packaging constructed of other than plastic materials must be subjected to a 24-hour stack test. A top load equivalent to the maximum permissible gross mass is loaded onto the top of the IBC. The test may be performed using a superimposed test load or dynamic compression. It is permissible to use a dead load such as coils of steel or 2 or 3 IBCs. This illustration shows stack testing with a large dynamic load compression testing apparatus. Upon completion of the stacking test, the IBC is emptied and subjected to leak-proofness testing. The IBC is filled with air, and a soap solution or oil is squirted over the seams and connections. Next, the IBC is pressurized to 20 kPa and observed for leaks. The final test on the IBC is the hydrostatic pressure test. The IBC is filled with water and pressurized to the specific test pressure, which is based on the vapor pressure of the intended lading. The test pressure ranges between 70 and 100 kilopascals, although generally the test pressure is 100 kPa. The test pressure is held for 10 minutes, and the IBC may not be mechanically restrained during testing. In order to pass the test, no leakage or rupture can occur during the test period. Next, we will discuss reading the IBC UN Mark. The first character must be the UN symbol, lowercase Arial font U and N in a circle. Next comes the packaging design type. The packaging design type for a composite IBC is 31HA1. Next is the packing group for which the IBC is authorized, Y or Z. A packing group Y authorization allows packaging of group Z materials. Next is the month and year of manufacture. Month and year is an important number, since the IBC must be inspected and leak tested every 2.5 years or 30 months. Also globally, plastic packagings, drums, IBCs, jerry cans, etc. must be destroyed at 5 years of age unless they are filled. This is not required in the United States. After the month and year of manufacture, the country authorizing the mark, such as the USA or other country of authorization, is required. The next item in the mark specifies the manufacturer of the IBC. This mark can be a manufacturer number or a third-party lab number. Most manufacturers have an M number that is tied to the manufacturer and its address. A manufacturer may also use their complete name and address if desired. Some manufacturers prefer to use their corporate logo or symbols if it is registered with the Department of Transportation. In some cases, you will see a third-party laboratory mark such as +AA. This symbol indicates a specific third-party test lab and will also include a file number that is unique to that packaging and to that particular manufacturer. After the manufacturer's mark, next is the stacking load in kilograms. This figure is obtained from the stack test and a multiple of the maximum permissible gross mass and will normally be between 3,500 to 4,500 kilograms. Next comes the maximum permissible gross mass in kilograms. IBCs are not authorized by specific gravity. Since they are bulk containers, IBCs are authorized by mass. With this particular IBC, 2,068 is the maximum allowable mass in kilograms, including the weight of the IBC. Next, you will see the rated capacity in liters at 20 degrees centigrade. In this example, the capacity is 1,041 liters. That's followed by the tear mass in kilograms, the gauge test pressure in kPa, and then the date of the last leak-proofness test and the date of last inspection. On a composite IBC, the inner receptacle or bottle must also have the code, M number, date of manufacture, and country authorizing the mark. This slide provides a summary of the required markings on IBCs. In addition to the marking we just discussed, additional markings are required on IBCs. IBCs must have an in-transit sticker or embossment on the label plate. The label will indicate no stacking or a weight in kilograms that is the allowable top load during transportation. A typical weight is 1,650 kilograms with the OK icon. This indicates you can stack up to 1,650 kilograms on top of that IBC in transit and transportation. This is a required UN mark and cannot be obscured, obliterated, or covered over with labels. Permeation barriers are used in IBCs because the barrier can provide a resistant layer to the plastic inner receptacle to prevent escape of potentially hazardous materials. Both the UN guidelines and DOT regulations specify the allowable amount of permeation a plastic receptacle or container can exhibit. The DOT regulations allow 2% weight loss of the lading, except for poison materials, which are allowed a 0.5% weight loss. It should be noted that the UN weight loss is a little less, but they do not differentiate standard permeations. Permeation barriers protect the entire container from softening and weakening of the container walls, avoiding container paneling and stack collapse. Barriers can also protect the plastic from stress cracking agents, reducing the likelihood of leakage and failure. Some barriers can also reduce the permeation of gas, oxygen, carbon dioxide, and water vapor, which can degrade food, pharmaceuticals, and other sensitive chemicals. A typical barrier that can prevent permeation is EVOH, or ethylene vinyl alcohol. The barrier material is sandwiched between the layers of the HDPE container using a multi-layer extrusion machine. Another type of barrier is nanosilicates. This barrier is more popular in Europe and Asia than the USA. Nanosilicates are a compound of nanocrystalline quartz and a polyamide that is added to the entire inner plastic container and blocks the migration of permeable material by providing a tortuous path. The silicates may inhibit recycling of the plastic. Another option is called advanced engineered polyamides. These are either monolayer or multi-layers of engineered nylon that inhibit the permeation. Polyamides can be mixed with nanoparticles. They can also be supplied with an FDA-compliant optical tracer. They are easily recycled. This is an illustration of a 5-layer barrier technology that incorporates a barrier layer such as EVOH. The cross-section of the wall shows the layers of high-density polyethylene, 2 layers of adhesive, and the EVOH barrier. Over time, there can be some degradation of the inner product content as the material dissolves into and through the HDPE, dissolving some of the adhesive. Use of the EVOH layer does inhibit the reuse of the plastic as well as the reuse of the container, whereas some other barriers do not. Using another barrier process, barrier resins are introduced by the masterbatch and a single hopper mixer processing technique. During the extrusion process, the barrier layers are integrated into the HDPE as monostructure. There are several types that reduce solvent, vapor, and oxygen transmission rates, thus protecting against permeation into your valuable product and loss of volatile compounds and ingredients. Additionally, the barrier does not degrade. Fluorination is another common way to modify the surface of the HDPE and create a permeation barrier. During this process, the plastic is exposed to fluorine gas, which reacts with the surface of the plastic to form a fluoropolymer. This provides a permanent protection against solvent migration. Fluorination is usually done by an outside contractor. Many levels are available to meet specific needs. The fluorination process does not hinder the reuse of the resin or recycling of the IBCs, but it also does not protect against water vapor, carbon dioxide, or oxygen. Flammable and combustible liquids are authorized in standard plastic IBCs for transportation as long as they are Packing Group 2 or 3. Packing Group 1 materials are not allowed in any IBCs. Storage is another issue. For information on storage, you should reference the National Fire Protection Association or NFPA Code 30. An NFPA Class 2, 3A, or 3B or those materials with a flash point at or above 37.8 degrees centigrade or 100 degrees Fahrenheit, can be stored inside in accordance with the proper protection scheme as long as the IBC is tested and listed by UL or Factory Mutual. When using IBCs with flammable and combustible liquids, the risk of electrostatic charge accumulation is greatest during filling and discharge. Comprehensive static control programs must be implemented by using grounded and bonded equipment. The operators must wear static dissipative shoes and gloves. An operator can hold enough energy and discharge that energy to the IBC, which can result in a fire or explosion. The use of antistatic, conductive, or fire-protected containers will minimize the risk. Antistatic IBCs are in conformance with the IEC, International Electrotechnical Commission, and CENELEC, an EU standards organization. This type of IBC is available globally. This IBC is a multi-interlayer receptacle, which incorporates an external layer of permanent antistatic compounds. The IBC is on a conductive pallet made of either steel or conductive plastic. The valve must also have grounding capabilities, as flowing fluids create static. This type of IBC is approved for use in explosive zones 1 and 2, but is not flame resistant. This type of IBC meets the UN model regulations for transport of dangerous goods in any class, but also for the transportation of combustible and flammable liquids with less than 60-degree flash point, as required in Europe. Further protection is gained by taking that antistatic IBC and putting it in a protective casement of some sort. IBCs can also be tested and listed or certified for use with flammable and combustible liquids. UL 2368 certifies IBCs to being in conformance with NFPA Code 30. The IBC would be a UN Certified Static Dissipative IBC for use in explosive zones. The IBC would also be in compliance with NFPA Code 30 for flammable liquid storage in inside unprotected storage. NFPA stands for National Fire Protection Association, but it is not a regulatory body. The NFPA writes codes that can be adopted by governments or agencies, such as a state or a regional fire district. The IBC has fire or flame protection of the inner receptacle via a two-layer woven fiberglass textile fabric with a permanent antistatic water-repellent layer. The top cap and bottom valve are completely covered and protected. Alternatively, the IBC can be encased in an insulated steel container without bottom valves. The UL 2368 exposure testing is conducted at the Underwriter Laboratories in Northbrook, Illinois. The test requires 28 days of storage with a mineral seal oil, a permeating solvent that increases the flammability of the plastic. During the test, the IBCs are double-layer stacked, with one IBC on top of the other. A 2-liter per minute heptane fire is the source of ignition, and the test runs for 20 minutes. The fire will reach about 800 degrees centigrade. During the test, the IBC may not burst into flames or leak. The stack may not tilt more than 5 degrees. After the test, the IBC is observed for 24 hours for signs of leakage. It's important to note that the UL-rated IBCs are required for storage of flammable chemicals. Listed IBCs are not required for the transportation of flammable chemicals. The storage location determines the compliance requirement. The recipient of the IBC must comply with the storage requirement. The shipper must comply if they store the IBCs longer than 24 hours prior to shipment. Although adoption of the NFPA Code 30 can vary from state to state, local municipalities may have incorporated the requirements into law. Any questions, you may contact Susan Nauman, Executive Director, at snauman@industrialpackaging.org, 410-544-0385.